The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I'm geologist Philip Ong, here with Mr. Dane DuPont, bringing you guys another volcano update. Today, Friday, May 7th, we're talking about Maunaloa volcano. And we're showing you guys here a view from the southeast rim of the summit caldera here, which is actually fairly visible. We had a winter warning today, but in the end, no activity up there. It's been clear days, and start off by showing you guys here some of these different views of the volcano from the USGS webcams here. And it's been pretty quiet the last couple weeks on the volcano. Last week has been quiet as well, especially with the earthquakes. We'll talk about how the GPS is doing essentially the same as it was before, and then we'll answer some questions that collect as he mans our chat and answers whatever he can on there as well. So here down from Kilauea, you guys can see the webcam view a lot cloudier down here at 4,000 feet elevation than up in the higher elevations of the volcano. Here's a southwest rift. It's a little bit different views here today, since there isn't as much earthquakes to talk about. I'll show you guys some more of these visuals here. Those are the views from the volcano today. A little bit of precipitation down there at the bottom. And I wanted to focus today a little bit more on some of our signals. So today we're going to be looking at signals quite a bit more. So deformation signals for the last week here in a volcano. We're just seeing our up and down day and night cycles. And there's a pretty big temperature variation at the summit of Maunaloa, so that's a common thing to see. It also can be seasonal variations, and in fact, that's part of the whole bunch of noise that exists up there that makes it hard to see other signals in a volcano, as we'll talk about here today. So over the last month, ignoring the smaller diurnal, as they're called, the everyday variations, you can see that there's maybe a slow pattern of rising and a slow pattern of falling, and something like that. Very, very subtle changes, right? Really within a range of half a microradian. Hard to really say anything above that, and really within the noise, within this range of variations in the everyday thing. So hard to take much out of that. There could be some volcanic signal in there, but it's hard to dig it out. And part of that is because Mauna Loa has essentially two different levels of volcanic plumbing. It's got a more long-term deep plumbing system, and then once in a while it seems like the shallow system gets occupied as well. And really, tilt is best suited for the shallow system monitoring, right? So we'll get to that here in the details a little shortly as well. But as far as our signals, not a lot to change in the tilt. Here's a GPS, and if we zoom in on the last end of this 1 year graph here, you can see that we are still in a perhaps a slight contractional trend. And this is the line of GPS across the summit of the volcano. Right, and it's worth pointing out to you guys. Let me come up here. There's a map. So across the caldera, MOKPs are stationed in the north. MLSP is stationed in the south. So we're looking at this essentially a north-south distance measure here. And we'll show you guys how in the past we've not only measured this distance, but also we've measured this distance over here, or the distance over this way as well. And so this is not the only way to measure it, but this is what we have automatic on the HVO website. So that's what we're basing a lot of our interpretation on. So we're going to put that in context here today as well. So really it's been, for the last 2 weeks, slight contraction, maybe slight extension a week before that. So it's really been it's been a while since the last week of March when we started having this dropping down signal, this contractional signal coming up. And this is one, just to point out, that followed a similar one we had in late October, early November, which you can see that in that case it dropped down and it stayed in that not extending, not contracting phase for a while, really until mid-January or so. And so these that can last a while, a month, 2 months kind of thing. So, it's not surprising to see this. It's more of a question of what's going to happen afterwards. Are we going to resume upwards like we did in mid-January, or are we going to have something different that resembles more of the earlier plots? Like in 2015, where we had, it's hard to see it on here, but we had a hump coming up, and then it came back down again and essentially stayed flat for a while. And looking at the 5-year plot down here at the bottom, that's the kind of the flat that we're coming out of and slowly building up. And here's 2018 era, and then really post-2018, extending much faster. And one little blip, that's that one in late October, November, and the one we're having just right here. And so that's the shape of it right now, as we sit today on May 7th, 2021. All right, so there's another axis, component axis here, which is a vertical, and looking just at that southern station here, we can see that no longer are we rising as well. We're essentially dropping down. This is a vertical component dropping, and that happened also earlier last year, the end of last year. So, and a 5-year view of that. So that's what the GPS we have today. And that would be really most of what we had to talk about without a whole lot of new data from the USGS. But this week there is also, besides a regular volcano update, we also have a Volcano Watch article. So let's recap the text that the USGS is giving us here this week. As far as the main update, the weekly update, there's not a whole lot of information in here. 118 earthquakes, small magnitude, under the summit upper elevation flanks. That's a little bit lower than recently, in fact, but still, still in that elevated background range. All less than magnitude 3, and all mostly at depths less than 5 miles above ground level, below ground level. I'm sorry. So in that upper portion of the volcano, as they have been recently. GPS shows slow rates of deformation over the past week, and gas and webcam views and temperatures are all stable. And that's what the summary of that last little bit there. So where is? Not sure. I actually have up here. So let me go here to the front of this. Oh, no, yeah. Let's look at the last week earthquakes here. We're going to turn to the Iris Earthquake browser here, and I have selected, you can do all kinds of selections here on the right. I'm selecting just the last month here. I'm sorry, just the last week here, last 7 days here. So over the last 7 days in the volcano, there really hasn't been a whole lot of activity. I have it animated here for you guys in a loop. And all right, so you see there's a few earthquakes up here in this upper Kawiki area, a few in there. It's a little bit more. We didn't have any there last week, so that's interesting to see that that's activating. And a few down here in this Hileia zone, and a few over here in this Kona zone, and a few over here in this northwest flank zone. But really, there's not very many anywhere. Right? That's just the overall pattern here. So, just to remind you guys, I'm going to put this up here one more time. This is from Walter and Amelung 2006, when they're linking earthquakes and eruptions and just movement of the volcano in general. So the point of this is the Kawiki area corresponds more often to the northeast rift zone area in here. The Hileia area and the Kona areas both often correspond to southwest rift zone activity here. So right now we're having it on both sides. It seems like we have summit and we have a little bit of northeast rift zone activity, and we do have a little bit of southwest rift zone as far as the filling locus near the summit. And this is not to say that there's any imminent indication of anything progressing beyond the summit. I'm just saying what these associations normally are. So as we try to pick out in detail here what's going on in a very minutiae of it, we see earthquakes in this Kawiki area. We can say, oh, maybe the northeast rift zone is filling, and magma is able to find its way in there and find some space. And we see the Hileia and the Kona areas activating, then maybe we have some space for it to move into the southwest rift zone area. And that's not surprising. The magma moves in there all the time without erupting. In fact, the most recent episode was this past decade is modeled to have filled the southwest rift zone area. And before that as well, you know, the intrusion from early 2000s as well is filling this upper area and a little bit of the southwest rift zone upper part as well. Okay, so the last week, looking just at the summit, is shown here. You really don't see a whole lot. That's really quiet compared to what it was the previous third week back and beyond that. So looking at the rates here for the past year, this is earthquakes by week on the left. The highest value on here is about 270, maybe somewhere in that range, and that was the first week of April here. So about a month ago, and you see that since then it's been steadily declining. Right? This earthquakes per week. Our current week here, we're not really all the way completed, but the previous one was down from 1 week before that, which was down from a week before that, which was down from a week before that, and these three being the elevated flurries that you really can't see at this resolution for the past year. You really gotta come down here to look at the past month, and in a past month we can see the tail end of the last two adjustments there and there. And these are, once again, to remind you guys, just earthquakes shown up here within this summit square right in here. So within the last month, here is where those earthquakes on that west flank, northwest flank, are located there. Okay, and they're colored by depth. So this is colors showing the depth being within that upper elevations and upper elevation flanks. All right, so the Volcano Watch tells us a little bit more. And the article is titled this week, Tiny Changes at Maunaloa Summit Hold Big Clues. And I'm not going to read all of it, but there are some parts that are worth recapping to you guys if I can kind of scan it here and show you guys here. So they do say rumblings arguably began in 2004. That was that first pulse of magma that was documented that we've talked about before. And however, Mauna Loa returned to its background state after that episode of dike intrusion within the volcano. And modeled to be fairly deep, so not a very shallow thing that had a chance to breach the surface, but really far down, deep within the volcano. And that's actually interesting to note that we're able to detect and model these deeper changes in the volcano today, which we couldn't do back in 1984, in fact. So we'll come back around to that as well. But they do say here, in the past 6 months, there's been an uptick in... Let's try that again here. In the past 6 months, there has been an uptick in earthquake activity on Mauna Loa's west flank and changes in the pattern of deformation at its summit. These changes are small, sometimes barely above the noise, but they may be telling us that the magma system is evolving in important ways. And so that's really what it's all about here. Our end goal is trying to get some information about the magma system evolving on a volcano, right? And you've heard me talk about the deep and shallow thing already. That's what we're going to be getting at here. They mentioned technologies change a lot in the 37 years since the last eruption in 1984. Now we have GPS stations. GPS stations were installed continuously in 1996 across the volcanoes, so that postdates the 84 eruption, so GPS is a new thing, really. Tilt meters, we did have tilt meters, we have more of them, and we have different kinds and are upgraded and all that. And we now also have, they say, regularly analyzed satellite radar data, and we are still waiting for another increment of public release of that regularly analyzed satellite radar data. So hopefully that'll be coming soon and tell us about the bigger picture in a volcano here. Because we will have some unanswered questions at the end of today still, and that's one of the clues to get at those answers. So they do mention higher rate of sampling, greater sensitivities, we see more detail. So in essence, what we're seeing now is something we haven't seen before. And they note 3 observations that are particularly interesting here, two geophysicists as they note. One is the direction of deformation at the summit has reversed twice since October 2020, switching back and forth from an outward expansive direction to an inward contractional one. The most recent one only shortened by 1.5 centimeters, 0.6 inches. This is small, but the reversal hasn't been observed at Maunaloa with modern instruments, it says. So when I scroll down here, they have a plot on here, and this is 3 panels, and let's focus on this bottom one first. This is that summit distance line. I showed you guys a 1-year plot. This is now showing you guys a 5-month version of it. So similar thing, we're coming out of the October flat part here, and then we're rising, extending here, and then contracting, and now stabilized for the last 2-3 weeks here. Right, so that's what we'll look at in some more detail, is that pattern of cross-caldera change. The second observation was the occurrence of a small, shallow magnitude 3.2 earthquake in Moku'a Ve'oveo on March 6th. Using satellite radar, we're able to see nearly 10 inches of subsidence in a small portion, unusual for magnitude 3.2 earthquake, and indicates the fault may have slipped all the way up to the ground surface. That means that the fault actually broke the surface of the earth and moved rocks on the surface for them to move that much. Rather than most faults don't come all the way to the surface, and so that means there's a bunch of rocks above it, and so they bend and bow, but they don't move nearly as much as if you had it broken all the way through. You can just slide them past each other. And so that's an interesting thing to note there. The deformations extending all the way to the surface of the volcano, all the way to breaking the ground, in fact. And the third one they say is the smallest, but maybe the most meaningful, which is that beginning on March 23rd, a tilt meter near the summit recorded a change of about 5 microradians, which is not unusual for Kilauea, but they note there has never been a volcanic here, let me read it exactly. There has never been before a tilt signal that could be attributed to changes in Maunaloa's volcanic system. Changes in tilt have been observed due to daily or seasonal temperature changes because of the rainfall, because of the rainfall, but never before due to volcanic deformation. So we'll put this in context. This is, I would add on there, not associated with an eruption, right? At least not yet. So, here is the key thing, and I'm going to dig into this after I finish this last little bit of text here. These new observations are interesting because they suggest some of the deformation is driven by shallower processes than we have seen in the past several years. That's the key thing right there. Shallower processes than in the past several years. But because this is the first time we've observed this level of detail, it's difficult to know what the data might indicate about the volcano's future. And finally, Maunaloa may become quiet again and return to background like it did in 2005, or it may not. So no conclusion there, but clearly they're suggesting that they have seen something similar to this before 2005, and we did go back to background at that point in time. We're a little bit different. We'll compare it here for you guys as well. So looking in more detail at this plot here, the tilts in the middle, we'll look at that here at the end, but the signal, there's daily variations are small here. This is 5-month plot once again now. And it's this signal right in here, right? This downward slope, which corresponds to the summit caldera distance as well. And at the same time, we have those episodes of seismicity on the west flank of the volcano, on the northwest flank, near the summit magma chamber, right? So when I showed you guys the last month plot, we were looking at just this right here. And I can put it back to remind you guys. Oh, that's the past year. this year, and down here, past month. So the last two humps there and there that correspond to those two right there. Right? So previous to that, back to January, it's pretty quiet. If you go back a little bit further, back to October, you do get a little bit more. Actually, in December, you get a little bit another spike back in here. We'll look at that a little bit here too. But to show you guys what this actually is, these three little bursts right in here, northwest of the summit, what are they talking about? It's these earthquakes right in here. Here's Maunaloa Summit, Caldera, Moku'a Ve'oveo right in there. And these are the zones of the earthquakes. So I've actually limited my earthquake plot right here. Let me zoom it in. Just that area. And let me animate it here so you guys can see. Okay, so I've got it back to October, right? So this is October. In October, pretty quiet still. November, pretty quiet. Here comes December, and we have a first little flurry in December. And then quiet, quiet, quiet. A little bit of background, a little bit of background. February, March, late March. There's a first cluster. Middle March, second cluster, third cluster, all through there. And so I put it back to here again, right? So that's the first cluster, second cluster, third cluster. Hard to see here, but if I actually have an automatic plot on here as well, and if I zoom into it, you can see here a little histogram with those three peaks. 1, 2, 3 there, and here's the December smaller peak that exists as well. So that's what they're talking about there. And I can get my browser to respond. We will move on from here. Just that one's going to get sacrificed. Oh, close one I didn't. All right, so let's bring this one back up here. All right, so still relating to earthquakes, the USGS released this interferogram at the end of March here, and they are outlining, in fact, this whole area of broad summit inflation, right? All through there, right? And notice that this is a bigger area than we can detect from that summit GPS line that moves from here to here, which is all within it, right? That line would be great for detecting something that occurs in there, where it's fully within the boundaries. But because that whole entire line is within this broad deformation field, that makes it a little trickier. However, the biggest signal on here is not that, is in fact, as if we zoom in, or zoom in more, please, right through there. You can see this bullseye pattern right in here that relates to magnitude, what was it? 3 point something earthquake here, shallow magnitude 3.2 earthquake, and something like 10 centimeters of deformation. So that's where they're saying that perhaps along this caldera wall right in here, right? This seems like it's very close to right in there. That maybe that caldera floor was able to rise and pop up. And so that's how much pressure was being pushed from below. So that's interesting, and that's something that was noted before. But you add it to, as an evidence of shallow deformation. For you to put pressure at that shallow level of the summit, we imagine you must be perhaps filling that shallower part of the volcanic system. And to maybe recap for you guys, Maunaloa is thought to have a shallow magma chamber somewhere under the southeastern rim, somewhere around here, right? And also a deeper system that's more of an elongated dike that's more of this direction, right? This. And so deeper, it fills this more planar, tabular space, but coming shallower, somehow it works its way over here. And there's a, maybe not right there, maybe it's more here. And so there's a shallower, more of a reservoir-like body. Right? And we'll come to why that's believed as well here shortly too. So earthquakes, that's one of the points of information here, a little bit more information on the HVO thing. And now we'll turn to this Summit GPS extension line here. So what I want to show you guys here is this first, we're going back to, this is a paper from 1983 from Bob Decker, former scientist in charge HVO. And this is before GPS, so there were different ways to measure deformation in a volcano, and one of those is electronic distance measurements. And that was started back in the mid-1960s on Mauna Loa. So we did catch the 1975 and 1984 eruptions with this technique. But anything prior to that, which was the last eruption was 1950, that's all lost. We don't have that information for that period of time. So what we do have, this is the change in 1975 right through here. And you can see these different lines, line 2, line 3, line 6, line 303, and 305. These are all different traverses, different angles of measuring it. So let me switch it over so you guys can see here. And so here's a location map. And HVO 93, aka MOK as it's known today, that's stationed at the north tip. And here is the one at the south, MLSP. And so line 6 is the equivalent of what we're measuring with our current Summit GPS distance right there, right? Is that line 6. So what I want to do is show you guys how, if we look here at this was in the build up to the 1984 eruption, and this paper essentially was saying, hey, within 2 years, an eruption is likely on Maunaloa, and here are all the signals showing why. And so not only did you have the big jump through 1975, but after that eruption, you had continued extension of the caldera, line 2, line 3, right? Those are the ones here and here. And so they're extending without any kind of big hiccup. But what I wanted to point out is that line 6 here has this little interesting little wiggle here at the end, right? Line 6 is actually showing a little bit of contraction, right? When everything else is showing extension, right? And signals of consistent with inflation of the volcano, right? So there's something funny happening right there. And it might have something to do with the fact that this station may be directly over top of this shallow magma reservoir right in here. And so if the reservoir fills more on this side, it can get pushed that way. If it fills more on this side, it can get pushed this way. And it's essentially wiggling right above it, and it can possibly teeter in any direction. So that's a possibility to consider right in there, is that this may not be I mean, it gives you more information, but it gives you a multiple set of information, not only the distance measurement, but also something about the inflation or movement of this more shallow storage area right through here. Okay, so the reason this is important is this is the prediction for 1984. They say, okay, it's 1983, and we see a shallow center of uplift from all our modeling. Magma is building in a shallow area right under here. Right? So that's their center of uplift right in here, and so that's how come you can have this station maybe getting an opposite direction of where it might go. And if we look here at their cross-sectional version of this plot, right, you can see there's present center of pressure marked on there in 83. Go straight up. And this is east of the caldera, southeast of that caldera. Right? So a station that was here would get pushed that way and actually contract the caldera. Right? So that's what the nuance of that southeast side right there happens to be. Right? So that's in these zones, this is the zone of lack of seismicity. So you might have some smaller magma bodies attenuating through here, but essentially some larger pocket in the middle, and then you have your dike system that's further down in here somewhere. And likewise, you might have multiple pathways of it, and the seismicity essentially dies off at the edge of these zones. So this is not exactly the size of the magma reservoir, but it's the size of the seismic shadow, so to speak. And somewhere smaller than that is the zone of actual magma storage, right? And you can also have interesting things where, if you imagine, let's say that this magma body has a top that's inclined in this direction, perhaps, something like that, then it could actually be that as it inflates, the center of inflation can move south and north over time. And that's something that has been documented in past eruptions, and that's kind of getting in the weeds, but I just mentioned that is a possibility, and that's something people do track, geologists do track, right? And that's part of this whole geometry problem as well. So the point being that during times, this paper, was preceding 84. This is the volcano, in hindsight, we know is going to erupt, right? It's going to erupt, and yet we still see a little contraction on this one line, but extension in all the other ones. So it's interesting that we see on the current GPS extension or line, the small contraction, but I'd be curious to see these other lines as well. And of course, we did these different lines back in the day because that was the only way to get a broader area. And so another way to address some of this might be the INSAR. If we had a broader INSAR that could detect changes across parts of the volcano, maybe you can do without using these lines and get similar kind of information there as well. All right, so let's keep moving in time. This is 1983 right in here. So if we iterate forward, oh, that's not it. Here it is. Iterate forward, we can see that there was an eruption in 84. And if I zoom in here, and this is this dark blue line is one we were just looking at that has a little dip. It dips down here before it actually shoots way up prior to the eruption, and then the eruption relieves it as we have in fact, it's a summit to northeast rift zone sequence, and it complicates the pattern there as well. But the point essentially being that we have an interesting little wiggle here, measured not through GPS, so never seen before in GPS, but possibly seen in EDM. And this is something that you really don't see much mention of within the literature whatsoever. It might have just been a complication that was, not easily explained, and so no one tried to explain it in anything published at the time. And so here we are. This is that dark blue line, which is your EDM to MLSP. So that's MOKP to MLSP, this station. But they also are showing this farther east to HO92, right, in the light blue. And you can see correspondingly, the light blue doesn't really show that contraction, maybe a tiny bit, but nothing really like you're seeing over here. Right? In fact, you might consider it to be flat with a noise right in here. Right? So, and unfortunately, this MOKP to MLSP, this line that does dip, if you go before 75, it's hard to tell what happened there. We don't really know prior to these three measurements whether there was points that were higher up or were the points flatter down. It's just a big unknown right there. Right? The station we do have information for going back in time doesn't show that any kind of little dip, really. Maybe something very slight in there, but within an error and a range from before. So you can see, depending on how you look at this, you may not be sensitive to that signal. So that's telling you something extra about that particular location right in there. Right? So this one's taking us forward through 2005, and shown in here in red is the beginning of the GPS signal. And so they're transitioning from EDM to GPS. And so this graph published by Thalen et al. 2017 kind of updates it here. And so you can see at this upper part of the graph here, this is that same MOKP to MLSP station. Blue is EDM, so there's our little dip before the 84 eruption. There's our missing who knows what before the 75 eruption. We really don't know. And here we're transitioning to the red being the GPS measurements, right? So rather than being really jaggedy, because really you had to have everyone hike up there. The whole crew's got to hike up to Maunaloa and occupy these old traverses and go measure everything. So each plot, each little point here is a trip up to that network station and a leveling survey that's done essentially there, right? A lot of work. A lot more work than installing a GPS station and having it radio the data back to you, right? And you actually get it all the in-between information as well. So when they say we've never seen this amount of detail before, this is what they're talking about. We don't have the resolution going back in time to see the little wiggles as much as you might see them here. So could there have been more wiggles, variations in between here? Absolutely, but you just don't see them because there was no occupation and there's no resolution to see that there. All right, and this bump here in the upper right is worth noting. This is at 2015 activity. So I'm going to scroll down here to the bottom, and the bottom is showing us earthquakes per month, only within a small area near the summit, including that west flank, and really not much anything else. And we're also going only larger than 1.7. We're also going only shallow. So there's a lot of qualifications for this earthquake plot, but that said, you can see that prior to 75, there was a spike of earthquakes, in this case being plotted per month, up to 60 per month here, with those parameters before the eruption. And there was another spike up to 80 per month before the 84 eruption, right, with elevated activity at higher levels, not as steady as it was in 75. A lot of up and down and up and down and up and down and up and down. And that's interesting because that's what we're seeing now, that up and down pattern. So are we seeing something similar to 84? Or let's scroll here to the right. In 2015, we had a lot of these earthquakes as well. We actually got up to similar levels, right? We're at 30 earthquakes per month as well. In fact, higher background than before 84. But we now know in hindsight, this does not cause an eruption. It was an intrusion that essentially filled underground without reaching the surface. So it's still filling the volcano. It just didn't have to break the ground to do it, right? So that's a possibility as well. So of course, the natural question is, that's 2015. So I have tried to do my best to update this plot. And I've put in up here on the top an extension to match our current GPS. So our GPS is, I'm going to zoom it way in for it to look anything familiar. Right, there is our bend, our drop down from November, and our most recent one doesn't even show here at the end. It's kind of like that right in there. Right, so kind of small little changes in there. And the question then is, does that drop down keep going up? I'm going to zoom in some more, yeah. Or is it going to be like this one, where after going up, it flattens out more again? So that's, once again, what we have to wait and see. Scrolling down to the earthquakes, I tried to replicate those same parameters, and here is my resulting plot for the earthquakes. And you see 2015 ramped up, went down. 2018 is this little gap in here, and then after 2018 we ramp up a lot more. So our background is actually fairly elevated. Let me zoom it back out so you can see that it's actually comparable to before 1984 and to before 1975, right? As far as those levels are, right? But instead of having the sequence 2 eruption, we now have a more recent example of it having a sequence 2 intrusion with no eruption. So that's what the question is now, is are we in a sequence 2 intrusion, or are we in a sequence 2 eruption, or both, or what the heck is going on over here? There's some new patterns that we're detecting that we didn't see before because we have better instrumentation here. Okay, so we'll see. We don't have the answer to that. We'd love to see some broader data as well, right? So here is that past 5 years and that little wiggle right in there, and this is that where all of that fits. It's back into here, right in here. And it's matched to match the scale on the y-axis and the x-axis both. So it looks a little different for that reason. All right, so that's how the GPS line fits in there. And now let's turn to look at the last thing here. We've looked at the earthquakes in the flank, how that fits in that pattern recently. We've looked at, in more detail about this local line length here from MOKP to MLSP and this little contraction, and does that mean a volcano is going to stop doing what it's doing? And there's absolutely no guarantee of that, right? Especially if you only have this one line. And that's one thing we've hopefully put a little bit more into context for you guys here. The last thing is this tilt signal right in here. And of course, the statement that I mentioned as well is that this is the first. I probably should go back and read it exactly because I don't want to necessarily get it wrong. But where is it here? There has never been a tilt signal that could be attributed to changes in Maunaloa's volcanic system, right? And also in a caption, they say the first time a tilt change in Maunaloa could be ascribed to volcanic changes, right? So, then, as I said, I would qualify that with without an associated eruption. And the reason I say that is because if you go back to the paper by Lockwood et al., who were recapping 1984 Kilauea eruption. That began at a summit and then migrated quickly to the northeast rift zone here. This is a plot of their continually recording tilt meter. It's true, it's an older model. And you can see our scale is a whole lot different here on the left. Our scale here in microradians, 0, 10, 20, 30. So these are big ticks, right? So the onset of eruption is marked by this dashed line. So you can see that previous to eruption, we're seeing a big rise in the tilt, the north-south, and in a west-east, right? And I believe also, and they're up and down, as they believe this was magma ascending towards the surface rapidly. That's essentially what's causing this to happen. So you see this big swing and tilt coming up, And then after a few hours, essentially, the magma is moving from that summit area into the northeast rift zone area. And so you see a deflation of the summit area right in there fairly quickly as well. The eruption lasting way longer than this one day, the 25th of March here, right? So it's zoomed way into the first day of eruption here. So this is, technically speaking, a tilt signal ascribed to volcanic change, but of course it was an eruptive change of a giant magnitude. And this is not the nuance that HVO is talking about. They're talking about something in the order of, if I go back here, our scale here, from +2 to -2. That's 4 microradians, 4 or 5 microradians or so. That's a much smaller change to detect, right? And so, sticking with 1984, I'll show you guys this image here while I recap the findings of Johnson in his paper in I believe 1990 paper by Johnson, who was studying gravity on Maunaloa and was able to come up with some of the parameters of the 84 eruption. And the key thing is this, right? So I'll show you guys this picture here first. So I'll show you guys several views of the summit before. This is a photograph by Warschauer, 1940 cone oldest down here in the middle, 49 cone up on a rim, on that southwest rim of the caldera. The 75 fissure cuts across it like this, and the 84 fissure cuts across it like this and covers all the floor with lava, right? So I'll leave this to look at while I read some of these numbers here, because Johnson 1990 was able to calculate how much mass was lost as a result of the eruption, and the answer was 52 million cubic meters, right? That's not so 52 million cubic meters is a seemingly a big number. We can compare it to other volumes of kiloway eruptions, but the point is that regardless of what the number happens to be, that was only 30% of the amount that was erupted out of the ground, is the amount that was actually lost within the volcanic system. So that amount, that 50 million, is not the full volume of magma that fed the eruption. It's only the difference between what went out and what must have come in from below to replace it, right? And there's a couple key things here, is that in 1984, they could not resolve the depth of where the magma was coming from to feed this eruption. So they essentially conclude that magma came from a very deep reservoir system. They can constrain it to being, they believe, somewhere in a range of 15 kilometers or greater beneath the surface there. So that's halfway down to that hotspot zone, right? It's a long way down, that deep system. And that there is a quick enough ascent of magma that's pushing the stuff in the system towards the top, so that the eruption of 1984 lava was thought to not have really mixed with the fresh stuff, but have been pushed from below and erupted out, and then was replaced by the stuff from below. Right? It's interesting to think about that, of how when we look at the first chemistry of lavas coming out of the volcano, even with Kilauea now, we say, oh, it's got the chemistry of the stuff that was here before. Well, that's true, but in Maunaloa, they saw that it essentially was just getting flushed out from everything from below. And they never saw essentially that fresh magma from below, but they did see a spike of CO2. And CO2 is something that exsolves from the magma very quickly. So if the magma is coming up from deep and sitting for a while in that shallow chamber, it should lose its CO2 more quickly. So the fact that you see CO2 coming at the end of eruptions, not just in 1984, but also in 75 and also in 1950, every single time it seems like that happens. It seems like the pattern of Mauna Loa is you have a batch comes from deep down, it comes up through the system, pushes the upper stuff up into the shallow chamber. That stuff erupts, and then you have the adjustment and settling of the volcano afterwards, right? So that's the key thing there, right? Is that you have a much deeper system, and that's what makes the shallow changes so much harder to detect. And maybe that's why it's harder to detect a 5 microradian change of volcanic significance in Mauna Loa, because normally the magma system is so far down that you just don't see, you can't detect it, right? So focusing on 1984, in 1984 they saw that even though we now know in hindsight it was all caused from a deep rising of magma from that deep reservoir from below, that was manifested at the surface as inflation of the shallow chamber, right, on the southeast section. And that's what was detected. That's what caused all these earthquakes, and that's what led to the eruption, essentially. And so we still don't have an answer there, but we do hopefully have some context to say that the adjustments in the volcano may still lead to an eruption, as was a pattern before, or it may be a new era of intrusion like we saw in 2015, 2005, and it may quiet back down in background, right? And probably the last X factor in here is really the fact that Kilauea is to its southeast, and Kilauea is what's buttressing the southeast flank of Maunaloa. And Maunaloa, when it expands, it's almost always doing that from the southeast flank moving. The northwest flank, north flank, that doesn't move hardly at all. It's all the southeast flank moving to allow that area to expand and create space. So if the southeast flank moves, you can fill the northeast rift zone, the southwest rift zone. You can fill that deep magma system, as we believe happened in 2005, right? And we know that we've had earthquakes on the southeast, on the south flank of Kilauea, and Kilauea has been active. And so the question really is that last X factor there. What effect is Kilauea having on this? That maybe Kilauea is able to affect this style where we can have more of intrusions now, rather than having to erupt all the time, right? And in fact, it's interesting because this 83 paper, I'll close with this. This 83 paper was put out as a follow-up to a paper in 1975, because in 75 they had seen the summit eruption. We know the pattern of sequences of the volcano. In fact, 75, after the summit phase was over, there was earthquake migration to the northeast rift zone, to the site where eventually 84 erupted. So they knew then that was a likely spot of eruption back in 76, and they said, okay, 75, I should say. And the eruption was in July of 75, 5th of July. So they say, okay, so within the next 2 years, we should have another eruption of Maunaloa, and it should be in a northeast rift zone, right where these earthquakes have parked themselves. But instead, it took from 1975 to 1984. And it took 8 years rather than within those two. What might have affected that? Well, the biggest change on the southeast flank of Maunaloa, which is Kilauea, and southeast flank of Kilauea, was in 1975, magnitude 7.7 earthquake, which moved the south flank. That happened in November of 75. So you have to wonder if this November of 75 earthquake that helped Kilauea move to the south allowed Maunaloa to move more to the south, that made it more space, that essentially bought it more time to go beyond those 2 years to the full 8 years to cause that eruption, right? And that's relevant because now the south flank is moving again. We had a 6.9 in 2018. Did we create more space to allow more of this move, buy more time, so to speak, for the process to have this injection into the lower parts of the volcano and fill it up? And maybe what's happened is it's filled it up to the point where it reached the shallow chamber. We're seeing the shallow chamber filling as well. And what now? Does it just keep filling and spreading, or do we pressurize it enough to fill that shallow chamber back up, right? Which the shallow chamber is the one showing contraction now. So it has to re-inflate the shallow system, even though the deeper system may be inflating, the shallow one may not be. And that's what is the missing piece for what comes next for this story, is what happens in that shallow system up there. And that's why, in the end, seeing tilt signals that are shallow and seeing shallow earthquakes breaking the surface are important things. Right, so I'll wrap it up there and we'll turn to some questions. But that is the story this week of interesting observations on Mauna Loa.
Well, thank you, Phil, for going through all those details and a bunch of nuance in there. I do want to thank everybody that tuned in today. You guys really helped make this possible. If you appreciate this type of content, maybe consider sharing, subscribing, that kind of stuff. We also do. We also put our content on HawaiiTracker.com. Real good place to catch up with what's new on both of our volcanoes and other news and information from Hawaii Island. And if you are so generous as to make a monetary donation, we take those on HawaiiTracker.com/support. I do want to shout out some of those people that have been making the donations on there. Appreciate it a lot. Jenna K, Dave P, Lori H, Brian B, Robin M, Linda H, Melinda H, Mark D, Alyssa H, and Victoria D. Thank you guys so much.
Mahalo, everyone. Mahalo. It means a lot to us. It really does.
Yeah. Let's get into some questions then. So we have a few here. To start off with, Erix1, he's on YouTube, asks, how much does the structure of the magma chamber change during or after a large eruption? Even with no collapse, is there still significant change underground?
That's a great question. I don't know that we have a really great answer. We don't really know the structure of magma chamber at any point in time, really. So it's hard to tell how much it changes from one to the other. We're still very hand-wavy, even about Kilaueas, and Kilauea is very well studied. Right, so we didn't even know following 2018 if the whole chamber was evacuated prior to the modeling results. And in the end, the 2018 collapse of Kilauea might have been from as little as 11% of the magma chamber actually emptying. Right, so that leads to the other point that's important, is that many eruptions don't actually empty all of the reservoir, but rather only the excess pressure. Right, so when you lose the excess pressure, you still have magma left in there that essentially maintains a lot of that reservoir system and a lot of that structure as well. And an analogy I've used before is like a soda bottle or a pop bottle or a champagne bottle, whatever it happens to be. If you agitate it and you pop it and let all the gas fly out and it brings all the liquid out with it, there's always some liquid left in your container after the fact that's a little flatter than before. You just can't get it all out of there, right? It's the gas getting out, and the liquid just gets in the way. So a lot of the liquid stays behind in there, and that's an analog that helps us understand maybe how this works a little bit. Not perfect.
We have a $20 super chat from Andre. He says, love your work. Any worries about the southeast flank blowing out on the outside of the existing caldera with that shallower magma chamber and all, or is that still most likely to erupt within the larger caldera boundary?
Within the larger caldera boundary is still the most likely thing. Yeah. There's a lot of nuance in Maunaloa. In fact, Maunaloa has a second large caldera scarp that's to the south as well. So it seems likely that the caldera, as the south flank of Maunaloa moves to the southeast, it's carrying the caldera structure to the south, which is likely why the magma chamber is on the southeast part rather than anywhere in the north. That's likely everything is getting deformed in that direction, right? So there is actually another caldera wall to the south of there as well. That's not nearly as big, but that just implies that there's a lot of space through there, and in fact, you can have eruptions in that area that do essentially focus within a summit is the best way to put it, right? Because the fissure lines are often a few miles long, and wherever they come close to the caldera, that's where they end up being focusing into actually feed the eruptions. So quite often there are eruptions that are around the summit areas and feed down the flanks a little ways, and that's normal. And when it happens, I'm sure we'll all freak out, but that's normal. And they just don't go that far, really. And it's more about the rift zone eruptions that tap the bulk of the magma reservoir, that feed massive flows that can reach all the way to the ocean. Those are the ones we worry about more, not the summit ones as much.
Right. While we're speaking about magma chamber, JW asked, earlier this year, we showed a internal structure diagram inferred from the earthquake wave deformation caused by the liquids. How often is this type of model updated?
Well, so there's overall a big divide between what's modeled and scientists have as working models behind closed doors and what's publicly released. Right. So as we've seen, INSAR is measured weekly, but they mentioned that there's a lot of noise, and so maybe there's nothing that's really obvious to show. If that's not publishable, right? Because when USGS puts anything out on a webpage, that's being published. That's a public information service right there. So if you have something ambiguous, maybe they don't put it out, right? But that doesn't mean that they don't have it going on behind closed doors and they aren't modeling it. So the answer really is I haven't seen any update of it, but there are all kinds of hints of things happening as far as models, and there might be updates that are not published or not accessible to us at this point yet.
And whenever we talk models, no matter if it's for volcanoes or whatever, I always like to just throw out the quote from George Box: "All models are wrong, some are useful." Right, and that really does help guide me, at least on having some reservations about when I see a new model or anything like that. And to me, I think of these models not being too uncommon for grad students that are doing some project, and they try and do it themselves type of thing. But does it get released? Maybe, maybe not. Does it get accepted into the USGS as kind of the model that they're going to use? Well, that's a much larger step to get to.
Yeah.
So let's get in. All right.
Yeah. It's definitely complicated that way, and of course the model is only as good as the team building it, right? And of course, as Dan and I are both programmers, we know that even the best software has programming mistakes within it. So this is something you have to deal with. There's always some errors. There are always first order approximations, and that's why any good model, like a lot of the ones we're showing you guys, they're showing you not just what they predict, but the residuals of what's the difference between what we predict and what's actually observed. And if those are small enough, you maybe are comfortable saying, okay, well, it's not exactly a plane or tabular body. Maybe there's some curvature to it, or maybe there's this, or maybe there's that, and those little details that are not a second order features, essentially, beyond the fact that you have call it a 10-mile long dike that's 3 miles tall. That would be a first order feature, and a second order feature might be the curvature of it. Then you can start saying, okay, well, it doesn't exactly fit. This is probably the kind of thing that's going on down there. Best guess.
Yep.
Always.
Makes sense. So Richard from YouTube asked, what is the pressure of the magma in the vent just below the point where magma goes airborne and launched into the air? Is it consistent to the surface, or is there a place where the pressure isn't as high, or do we know anything about that?
Oh, there's a lot about that. I don't have it on top of my head. It comes down to the release of gas bubbles. It's gas that's driving the magma out of the vent, and so the pressure when it's building the highest essentially is being built by gas pressure. There was just recently, I want to say, this year, a study put out on the beginning stages of Ahu'aila'au, Fissure 8. On May 5th, I believe, there was that video that was studied by Manila guys, where they shot high-speed cameras at the fissure to try to characterize the size of spatter, the amount of spatter, the frequency of spatter, and get some exit velocities was one of the things as well. And from that, you can start building pressures, right? If you can start synthesizing all of that data. And in the end, it was you have bubbles of all different sizes. You have smaller bubbles, you have bigger bubbles, and depending on if you have a buildup of gas, that's when you have the highest fountaining events. So it really comes down to the gas involved, and I don't have an absolute answer for what the pressure is, but I can tell you that it's gas driven.
And also the nozzle, the diameter of the nozzle matters in that whole thing too, because Fissure 8 had a ton of pressure behind it, but it just didn't have that closed vent where it could get that kind of height, so it was able to relieve the pressure with a 100 to 200 foot fountain.
Yeah, and since we're talking about Maunaloa, that's a typical thing of Maunaloa, it seems, as well. You don't really hear as much of high fountains in Maunaloa. I mean, there definitely are they do exist, right? You see the 1940 cone and 1949 cone are big cinder cones that had to have had fountains, right? But a lot of the eruptions, because they have this fissure system that goes from the summit into the northeast or the southwest rift zones, you quite often can have that same kind of gravity effect where you don't have to, and you have a big crack, you don't have to shoot it out in the air thousands of feet. You can shoot up in the air hundreds of feet or tens of meters instead, kind of thing, right?
Right. We have a question from Jennifer on YouTube, on Facebook. Asks, why does USGS have stations, or why doesn't USGS have stations to measure the east and west distance across the caldera?
They do, and that's just not on a public side of things, right? So if you were to go into the HVO internal pages, you could see many more plots of distances and model results than are just on the website. The website, this website was put together like in the 90s, and a lot of the information put on there hasn't changed. hasn't been updated, hasn't been added onto, hasn't been augmented.
Right.
So I'm not complaining. We get a lot of data. It's great that we get what we do, but by no means is it the cutting edge data. That's just something we got to be clear about.
All right, that works. Let's go on to the next one then. This is kind of a general question. I'm going to extend it a little bit. Tia asks, what would you recommend for folks living in Puna areas, or rather anyone on this island? Should we be prepared for an upcoming eruption and be cautious, or just be open ear and ready for anything? Like, where do we stand currently?
Yeah, so as regards Mauna Loa, I mean, Mauna Loa is the reason we're talking about Mauna Loa all the time is because we want to think about the fact, people understand that it is going to erupt someday, and it's not going to be a surprise when it does. And if you haven't thought about what to do when that happens, then sometime you need to do that, right? That's the main thing, right? And there's no imminent danger of it happening for Mauna Loa, and when Mauna Loa goes, it's not going to affect Puna really. It's going to be of more concern to other parts of the island, right? But it's at this point a preparedness thing, right? Mauna Loa, when it does erupt, is likely to have a summit sequence first, which is going to be far from everybody, and then we'll have some time, more than likely, before we see patterns moving to one of the rift zones. And if it moves to one of the rift zones and dies off, then we have even more time. If it doesn't die off, then we know that there's something coming out of one of the rift zones sooner than later. In either case, we'll have some time to deal with that, and it'll start at the upper elevations before it works its way down, more than likely. So there'll be some time to deal with that at that point in time, and especially in Puna, right? But especially people who live in South Kona, this should be, it should be like living in Tornado Alley. You should always have a tornado plan. You just know what happens if you have 5 minutes warning for the tornado. And it's a volcano. You have essentially years of warning that something's going to happen someday, and it's just a matter of having thought about it and not freaking out about it and saying, okay, but just having emergency plans in general, whether it's for hurricane or for tsunami. Okay, if we're all at the beach and someone sees signs of tsunami or the siren goes off, everyone, rather than looking for each other, we all meet at this point inland, and we meet by the car, or we meet up by the house, or we meet at the house at the top of the hill, or what have you, at the beach that you go to. Or if I'm at work in Kona and someone else is in school and in Pahala or Na'alehu or something, then where do we meet? Those are the things in general, right? If Kilauea would erupt again on an East Rift Zone, and you were to, what is your plan, right? Are you gonna, do you have a place that you'd like to go, or do you have? Is there some, and I know there's a lot of trauma people in Puna, right? So is there something, maybe the best way to make it positive is there something that happened the last time that you'd like to do better the next time, right? So you can reflect on 2018 at some point in time, especially now, this week is the 3-year anniversary, right? So reflect on how things went 3 years ago, and what could be done different, from your end. Could you have been more prepared? Could you have gathered? Are there things that you wish you would have gathered, or someone would have told you ahead of time? And ask those questions now. That's why we do what we're doing now. Essentially, is to keep talking about that and awareness, and so that when it comes time that something does happen, the science of it isn't novel. It isn't like, oh my gosh, like where did this come from? You guys are hearing where it's coming from every week. Right, it's slow, drawn out, super slow motion process to the point where you might get tired of it and be like, oh, I don't have to worry about that yet. I don't have to worry about that yet. And at some point, you do need to worry about it just to make the plan, and then you can stop worrying about it until there's something else to worry about.
Right.
That's not too convoluted.
And
there.
just to throw out like one thing that I wish I knew before the 2018 eruption was just how after the lava comes out on the first day, that's the time to really go in there and act and get things done, because there was this thing like get out, and then people fled without any of their possessions, and then it was difficult to get back into the eruption site via the authorities, and so it created this unnecessary pain for people, for some, where they weren't able to evacuate, even if they had prepared put all their possessions on a trailer, right? Had that trailer in the yard ready to go. If they just bailed without the trailer and expected to be able to come back and get it, that didn't happen, right? So that was the one thing, I would be looking for next time is when it comes out of the ground, that's really the time to go in there and get things done. It's not, run away from it. It's not going to start out at its heaviest point. It's going to build up to get to that apex over time. So use that time once it starts. You got to get in there and you got to do the evacuation while it's going, but that is the time to really make sure to get things done.
Right, absolutely. Yeah, so that's something you can do from a personal end. That's something we also can lobby our local governments as well, that make sure that your neighborhood has a good evacuation plan, right? It's not just, okay,
Right.
we're going to have placards and everyone's out and no one's ever allowed back in ever again, right?
Right.
That you've talked about, okay, our neighborhood can divide it into these sectors, and depending on which sector, there's an issue in, and the egresses and, the traffic flow, like what makes sense for where you live, right? And, does your community have a response plan? Does everyone meet at your community center? And do you have, those kind of things, right? So I think if a local community is organized within themselves, it's a lot easier for whatever the government is, because it changes, right? Whoever's in government at the time, for them to help your neighborhood adopt your neighborhood's plan rather than come in and tell you how things should be. So I think it's really what we've learned from 2018, what I learned, from being part of the hub, is that it's the grassroots effort is much stronger and can mobilize resources much more quickly than the government can. So my advice, it's just that advice is, besides your personal plan, if that's not enough and you want to be more proactive than that, then help work on your neighborhood's plan as well.
Right. Richard on YouTube asks about using sound, ultrasonic, any type sensors to help monitor the volcanoes. Do you know anything about that?
So there is ultrasound that's measured. I don't know that there's any instrument really close to Maunaloa, but I think there's one on Kona that maybe, but I don't know that they detected anything like that. There are things called borehole strain meters, which do detect pressure as well within the pit, right? But in the end, it's fairly similar to I think the tilt and GPS fills that niche as well. So that's something that, even though it was done before, I don't have information to report on that now. I think those may even be still operating now. I'm not sure, those borehole stream meters on Maunaloa, but that does exist as well.
And running out of questions here. Yeah, let's do one last one. So what are the chances or likelihood or even ballpark approximations of a chance of a pyroclastic type eruption on Mauna Loa? This is a question from Beth on YouTube.
Okay, so pyroclastic eruption I'll just say it's highly unlikely, right? There have been explosions documented in Mauna Loa. They seem to be correlated with about the time of caldera collapse, more or less. All the debris fans of the ash clouds and blocks from Mauna Loa are all pretty close to the summit, within 2 miles of the summit, I want to say. So even if there is some kind of explosion cloud and some collapse of the debris field, it's not likely to be very big or go very far and affect anyone that way. And so
it's so big it'd be hard to even notice unless you were paying attention. Almost, if it was cloudy or something like that, it'd be socked in with the clouds. Be hard to know. If you didn't have the sensors.
Yeah, for sure. Yeah, and we will at some future point. I promise it is coming. We'll talk about the details of the explosions in Mauna Loa. Not going to do it quite yet. But when you consider that explosions of Kilauea are thought to have to involve either very gassy fresh magma or interaction with a water table, right? And you think about those things on Mauna Loa, yeah, you certainly can get a very gassy magma coming from very deep coming up. That seems the most likely thing to happen. But there have been caldera collapses. You know, we know there was some collapse likely in 1868 during that 7.9 South Flank Mauna Loa earthquake. That seems a good time to collapse your summit, right? So that likely happened then. I lost my train of thought there.
Oh, that'll happen.
It's getting late today.
Yep. And it's just go ahead.
Yeah, help me out here.
Well, the thing, just Mauna Loa and these explosive eruptions, you know, it's such a, you can never say, you know, it's not going to happen, but it's not something that Vegas is going to make a favorite. We'll put it that way.
Yeah. So here's what I was going to say. Yeah. We haven't found big ash beds near Mauna Loa summit like we have at Kilauea. Right, Kilauea, we can document the history of big explosions because we can see them. They might be in Mauna Loa just buried because there's a lot of lava up there, but we haven't found that yet. And if we found that, we might be able to see a lot more about Mauna Loa explosions going back prior to what we just find on top of lava flows now, which is, you know, lava flows of 1,000 years, 1,500 years old or so. The last thing I was going to say is if you consider the interaction with water, right, and a water table of Kilauea and a water table of Mauna Loa, there is water that's higher up in Mauna Loa. That's not a huge amount of it, though. Most of the water under Mauna Loa is a lot deeper down, right? So you think about interactions of magma and water, it's probably it's a whole different dynamic under Mauna Loa than it is under Kilauea, because Mauna Loa is so much taller, right? Not only that, the magma isn't... you know, the magma reservoir has this deep and shallow duality to it that we don't quite see on Kilauea. I mean, Kilauea has that the deep Kilauea chamber, as we call it, is, you know, what the range of 4 to 6 kilometers down or something like that. Yeah, or so it's, you know, it's not anywhere near the 15 that Mauna Loa's is. Right. So it's a different. It's not. It's like deep versus deep. They're not the same kind of deep. It's just relative within each system, right?
Well, I believe that does do it for all the questions today. I am going to be premiering another episode of Drones On, which is recapping the 2018 eruption on day by day. And we're going to be looking at May 6th, the day that Fissure 8 really took off on Luana Street. A lot of loss in this one, and the first real big lava flow that we saw in 2018. So I hope to see you there. That's going to premiere right after this live stream.
Yeah, right on. Yeah, so we'll try to put out an announcement as well, but it doesn't always show up everywhere. You might have to go on and search for it here. And that was an early foreshadowing. You know, that the biggest flow in that first week came from Fissure 8, and ultimately that was the biggest where all the lava was going to come out. It's going to be Fissure 8, Ahuelau in the long term as well. After that whole first 2 phases was passed, and we established that big pathway from the summit. That was an early hint, you know, looking in hindsight. Right. So
I also go through one of the things that really nobody but us talks about, that emergency alert that was put out on May 6th. That didn't make any sense at all, and just try and remember it, because, you know, if you don't remember it, then you're much more likely to make the same mistake next time.
Yeah, so most people who are not in Hawaii had actually heard of our false missile alert earlier in 2018, right? And then, you know, for those of you that are curious, as a little hook here, there was a version of that was for the eruption within Puna, a false alert that went out, and more than just false, dangerous, in fact. Yeah, I'm sure Dan will cover that.
Yep.
So check out. See you there. Yeah, for sure. Yeah, check that out. It's worth seeing. Dane's done a great job. Great job, Dane. Thank you for sharing. I know it's really personal for you. You know, a lot of that loss is personal to you.
Right. And the one thing that gets me is I just can't watch other people from outside the area talk about it, because they always are getting, you know, something wrong. I guarantee I'm going to make some mistakes in it, right? Because a lot of it I'm trying to go off of memory on. But it's, you know, trying to get the justice done just to preserve it for later. So when somebody's studying it, the way in which certain people want to remember the eruption isn't the only way that it's told.
Right.
Right. All right. Well,
Yeah.
thanks, Phil. Thanks for the presentation, and that'll do it for me here.
Yeah, mahalo day, and everyone check out the premiere coming up. Mahalo for you guys, all your great questions today, and mahalo for all your support. And we will see you guys next week on Tuesday for another live stream. We'll put out some shorter summaries as well. On Tuesday, we'll look at Kilauea once again, which is still erupting. And we'll talk about that on Tuesday. And come back to you guys next week on Friday for another Maunaloa update. Mahalo once again from Hawaii Tracker. He's Dan DuPont. I'm Philip Ong. Aloha, everyone.